The sun is the source of life on Earth, but it is also a mystery that scientists are still trying to unravel. Recently, they made a surprising discovery that the sun is emitting gamma rays, the most energetic form of light in the universe, at a much higher level than expected. These gamma rays are so powerful that they can only be detected by a special observatory in Mexico, and they raise new questions about the sun's inner workings and its role in cosmic phenomena. In this video, we will explore this record-breaking discovery and the story behind it, and explain what it means and why it is so special. Gamma rays are invisible to the human eye, and they cannot penetrate the Earth's atmosphere. So, to observe them, scientists need to use special instruments that can capture their faint traces in the sky. One of these fascinating instruments is called HAWC, which stands for High Altitude Water Cherenkov Observatory. HAWC is located in Mexico, between two dormant volcanoes, at an altitude of more than 13,000 feet. It consists of 300 large water tanks, each filled with about 200 metric tons of purified water. When gamma rays from space hit the air molecules above HAWC, they create showers of particles that travel at very high speeds. Some of these particles reach the water tanks and produce a blue glow called Cherenkov radiation. By measuring this glow, HAWC can determine the direction, energy, and type of the original gamma rays. Unlike other telescopes that can only observe gamma rays at night, HAWC can operate 24/7, which gives it an advantage to study the sun. The sun is usually considered a source of low-energy gamma rays, which are produced by nuclear reactions in its core or by solar flares on its surface. But HAWC discovered something unexpected. The sun is also emitting high-energy gamma rays, with energies up to 1 trillion electron volts. That's about 30 times more than the previous record for solar gamma rays. And these gamma rays are not coming from the usual suspects, like flares or sunspots. They are coming from regions of the sun that are relatively quiet and calm. How can this be possible? And what does it tell us about the sun? To answer these questions, we need to understand more about how HAWC works and how it can observe gamma rays during the day, unlike other telescopes that can only see them at night. HAWC uses a technique called indirect detection, which means that it does not observe the gamma rays directly, but rather their secondary effects on the atmosphere. This allows HAWC to avoid the interference of the sunlight, which would otherwise blind its detectors. However, this also means that HAWC has to deal with a lot of background noise from other sources of radiation, such as cosmic rays or atmospheric showers. To filter out this noise and isolate the gamma rays from the sun, HAWC uses sophisticated algorithms and statistical methods that compare the data from different tanks and different times. By doing so, HAWC can identify the distinctive signature of the solar gamma rays and measure their properties with high precision. HAWC is not the only instrument that can detect gamma rays from the sun. There are other telescopes that use different techniques and have different capabilities. For example, NASA's Fermi Gamma Ray Space Telescope uses a technique called direct detection, which means that it observes the gamma rays directly using a detector on board a satellite orbiting Earth. This allows Fermi to have a wider field of view and a higher resolution than HAWC, but it also makes it more sensitive to the sunlight and less able to detect very high-energy gamma rays. Another example is Solar Terrestrial Relations Observatory, STEREO, which is a pair of satellites that orbit the sun at different angles and distances from Earth. This allows STEREO to have a unique perspective on the sun and its activity, but it also limits its coverage and sensitivity to gamma rays. By comparing and combining the data from these different instruments, scientists can get a more complete and accurate picture of the sun and its gamma rays. However, they also face some challenges and discrepancies that need to be resolved and explained. For instance, HAWC has detected more high-energy gamma rays from the sun than Fermi or STEREO have. Why is that? And what does it imply for our understanding of the sun? We will explore some possible answers in the next section. How can the sun produce such high-energy gamma rays? This is a puzzle that scientists are still trying to solve. One possible explanation is that these gamma rays are not directly produced by the sun, but by cosmic rays that interact with it. Cosmic rays are charged particles that come from outside the solar system, such as supernovas or black holes. They have very high energies and travel across the galaxy at nearly the speed of light. When they approach the sun, its powerful magnetic field captures them and redirects them outward, away from the sun. The cosmic rays then collide with protons in the sun's atmosphere and create unstable particles called pions. As the pions decay, they create gamma rays. This theory sounds plausible, but it has some challenges and limitations. For one thing, it does not explain why the gamma rays are brighter in some parts of the sun than others. For another thing, it does not account for how the cosmic rays can escape the sun's magnetic field and reach Earth without being deflected or scattered. And finally, it does not match well with some of the observations made by other instruments, such as NASA's Fermi Gamma Ray Space Telescope or Solar Terrestrial Relations Observatory. These instruments have detected different patterns and energies of gamma rays from the sun than Hawk has. So there might be other factors or mechanisms involved in producing these gamma rays that we don't fully understand yet. Another possible explanation is that these gamma rays are produced by a process called magnetic reconnection in the sun's corona. The corona is the outermost layer of the sun's atmosphere, which is extremely hot and tenuous. The corona also contains twisted and tangled magnetic fields that sometimes break and reconnect with each other, releasing huge amounts of energy and accelerating particles to high speeds. These particles could then emit gamma rays as they collide with other particles or magnetic fields in the corona. This theory also has some merits, but it also faces some difficulties. For one thing, it requires very high temperatures and densities in the corona to produce enough collisions to generate gamma rays. For another thing, it predicts that the gamma rays should be more concentrated near the solar poles than near the equator, which is not what Hawk observes. And finally, it does not explain why some of these gamma rays have energies higher than those expected from magnetic reconnection. What are the implications and applications of this discovery? This discovery is important for several reasons. First, it reveals a new aspect of the sun that we didn't know before. It is a source of very high energy light that can tell us more about its structure and dynamics. By studying these gamma rays, we can learn more about how the sun's magnetic field works and how it affects cosmic rays and other particles in space. We can also probe deeper into the sun's atmosphere and see how it interacts with different forms of radiation. Second, this discovery opens up new possibilities for exploring other cosmic phenomena that involve high-energy gamma rays. For example, we can use these gamma rays to study how stars evolve and die, how black holes form and grow, how galaxies form and collide, and how dark matter behaves. We can also use them to test some of the fundamental laws of physics under extreme conditions that we cannot recreate on Earth. Third, this discovery challenges us to improve our models and methods of observing and analyzing gamma rays from space. We need to develop better instruments that can detect these gamma rays with higher sensitivity and resolution. We also need to collaborate more with other scientists who use different techniques and datasets to study the same phenomena. By combining our efforts and perspectives, we can gain a more complete and accurate picture of the sun and the universe. Thank you for watching this video. We hope you enjoyed learning about this record-breaking discovery and the story behind it. If you liked this video, please give it a thumbs up and subscribe to our channel for more interesting and informative videos. And don't forget to leave a comment below and share your thoughts and questions about this topic. We would love to hear from you. See you next time.